Alright guys, remember when we did half reactions and we added the cell potential of each half reaction to get E cell? We figured out whether or not the reaction was spontaneous based on whether or not E cell was negative. What I didn't point out is that this is actually E naught cell. This is the cell potential if the aqueous components are at 1 mole per liter. And if we had gases, that the gas pressure is 1 atm. But that's going to be rare for you. 1 mole per liter aqueous solutions makes this E naught cell. Oh, and by the way, temperature plays a role as well. If you don't have 1 mole per liter solutions, you're going to have to use the Nernst equation to figure out your actual cell potential. It'll be close to 0.78, but it won't be exactly 0.78. These are your Nernst equations. Now there's 2 of them, and I don't know which one your teacher gave you, so you're going to have to figure it out for yourself. This one uses ln, or the natural logarithm of Q. Both of them start with E cell. Both of them have a subtraction. But one uses the natural logarithm and one uses log. Actually, one of them also accounts for temperature. If you have a temperature other than 25 degrees Celsius, you're going to have to use this equation here. If you have the same temperature, like 25 degrees Celsius, you'll use this one. Okay, E naught cell is the cell potential you found in your previous question when you added the cell potentials of each half reaction. R is the gas constant, T is your temperature, N is the number of electrons swapped each time the reaction happens, F is the Faraday constant, and Q is the same as your equilibrium value, or equilibrium expression, but with the actual concentrations. That's going to make a lot more sense to you when I do it for this reaction right here. We have copper 2 and iron making iron 2 and copper. Oh yeah, we already did this one. It's 0.78 volts. But that assumes 1 mole per liter. What if we had 3 moles per liter of copper 2 and 0.01 moles per liter of iron 2? Pretty good question. Different concentrations, use the Nernst equation. Now it didn't mention anything about temperature here, so I'm going to use this equation right here. E equals E naught cell minus 0.05914 divided by N times log Q. So, what do I need to fill in for my values? Well, E naught cell is what you found before, 0.78 volts, minus 0.05914 volts divided by N. N was the number of electrons swapped in the reaction. It's probably pretty clear from here that it was 2 electrons, but take a look. When we added the 2 half reactions together, we ended up canceling 2 electrons from the left and right. That means it's 2 electrons that cancel out, or that we divide by 2. What is log Q though? Q is your equilibrium expression for the reaction as it happens. Remember, that's products over reactants, and exponents become coefficients become exponents, and solids and liquids aren't included. What I mean is, if I was going to come up with KEQ for this, I'd need Fe2 plus the product. I wouldn't include my copper solid because it's a solid. And on the bottom, my reactant is Cu2 plus. I wouldn't include my iron solid. If there were numbers in front of here, I'd have to include them as exponents, but there aren't, so I won't. So what I end up with is the log of my iron concentration, 0.01 moles per liter, and my copper concentration on the bottom, that's 3 moles per liter. So I filled in all the numbers that I need right here, and now all we need is a little calculator to figure out what this value is. I'm going to start over here, 0.01 divided by 3. take the log of that times 0.05914 divided by 2. Now I'm going to have 0.78 volts minus that. And I get 0.853 volts. By increasing the copper 2 concentration and decreasing the iron 2 concentration, I actually get a slightly bigger voltage out of my battery. I guess that makes sense because I am providing a little more reactant and a little less product to start with. What's important to note here is that as the reaction occurs, the copper concentration will go down, this will go down, this iron concentration will go up, which will increase this value, which means I'm subtracting a bigger value each time, which means the cell potential will eventually reach about 0.78. But at the very beginning, it's definitely going to give me just a little more than that because my concentrations are so out of whack. That's how you use the Nernst equation to account for non-1 mole per liter aqueous solutions. Remember, you can use either of them, and this is the one you've got to use if you have to plug in your own new temperature. Hey, best of luck.